Section 9.6 Partial orderings. Definition 1. A relation R on a set S is called a partial ordering or partial order if it is reflexive, anti-symmetric, and transitive. A set together with a partial ordering R is called a partially ordered set or poset and is denoted by the pair SR. Members of S are called elements of the poset. Example 1. Show that the greater than or equal relation is a partial ordering on the set of integers. Reflexivity. A is greater than or equal to A. Anti-symmetric relation because these two inequalities imply A equals B, and transitivity is property that we know very well for real numbers. So it holds for integers also. Example 2. Show that the divisibility relation is a partial ordering of the set of all positive integers. Usually we denote this set with Z. The relation is reflexive because any positive integer A divides itself. It is because A can be written as A times 1. The relation is anti-symmetric because if A divides B and B divides A, then A is equal to B. From A divides B, we have B equals AC for some positive integer C. From B divides A, we have A equals BD for some positive integer D. Now replace here A with BD, then cancel out B. These here are positive integers and their product is 1, so each of them is 1. But here, if C is 1, then A and B are equal. So I prove that A is equal to B. Transitivity. A divides B, B divides C. It follows that A divides C. From the first relation A divides B, we have B equals AK for positive integer K. From the second, B divides C. C is BL for some positive integer L. And again replace here. B with AK. We have C equals AKL, which means that A divides C. So the relation is transitive and it is a partial ordering, so Z plus is a poset with respect to this relation. Example 3. Show that the inclusion relation is a partial ordering on the power set of a set S. The power set of S consists of the family of all subsets of S. For any subset A of S, A is a subset of itself. So the relation is reflexive. If A and B are subsets of S, and A is a subset of B and B is a subset of A, obviously A is equal to B. So the relation is anti-symmetric. And A subset of B subset of C implies that A is a subset of C. This is from the definition of a subset. So the relation is transitive, so the power set of S is a power set with respect to this relation. Definition 2. The elements A and B in a power set S with this relation, partial order. So two elements A and B are comparable if either A is less than B or B is less than or equal to A. A and B are elements of S so that neither A is less than or equal to B nor B is less than or equal to A. Then A and B are called incomparable. This symbol is stylized less than or equal is used to denote the relation in any power set. Definition 3. If S is a power set and every two elements of S are comparable, S is called a totally ordered or linearly ordered set. And the relation is called total order or linear order. A totally ordered set is also called a chain. Definition 4. A power set S is a well-ordered set if it is a power set such that the relation is total ordering and every non-empty subset of S has least element. Definition. Here I define lexicographic order. Given two power sets A1 and A2 with their relations 1 and 2, the lexicographic ordering of the Cartesian product A1 times A2 is defined by specifying that the pair A1-A2 is less than the pair B1-B2, either if A1 is less than B1 or if A1 is equal to B1, then A2 is less than B2. This definition can be easily extended to lexicographic ordering on strings. First on entuples and then strings. Example, consider strings of lowercase English letters. The lexicographic ordering can be defined using the ordering of the letters in the alphabet. This is the same ordering as that is used in dictionaries. For example, discrete is less than discrete because these strings differ in the 7th position for the first time, and E in the first string is less than the 7th letter, which is T in the second string. And this, the same or discrete, is less than discreteness because the first 8 letters agree, but the second string is longer. Hasse diagrams. A Hasse diagram is a visual representation of a partial ordering that leaves out edges that must be present because of the reflexive and transitive properties. For example, in A, we have the diagram of some partial ordering, some pole set with a partial order. And you see that at any vertex there is a loop. This is because the pole set has a relation that is reflexive. In B, all those loops are missing. Then this arrow from 1 to 3 must be here because we have an arrow from 1 to 2 and then an arrow from 2 to 3, and the relation is transitive. So any arrow that can be obtained from the transitivity law is omitted in B, and this way we end up with C, and here the arrows are omitted because all the arrows point upward, so we know in advance. For that reason, the arrows may be omitted and we have just edges. So the last diagram is called a Hasse diagram for the diagram of this pole set. Procedure for constructing a Hasse diagram. To represent a finite pole set S using a Hasse diagram, start with the directed graph of the relation, which means that for each element of S we place one vertex, and for each pair of the relation we draw one arrow. Then remove all loops that are present in the diagram at any vertex due to the reflexive property. Then remove all edges xy for which there is an element z in S such that x is less than z and z is less than y. These are the edges that must be present due to the transitivity property. Arrange each edge so that its initial vertex is below the terminal vertex. Remove all the arrows because all edges point upwards towards the terminal vertex. Maximal and minimal elements. Elements of pole sets that have Certain extremal properties are important for many applications. An element of a poset is called maximal if it is not less than any element of the poset. An element of the poset is called minimal if it is not greater than any element of the poset. Maximal and minimal elements are easy to spot using Hasse diagrams. They are the top and the bottom elements of the diagram.